come to the part that starts to be confusing. At least it was for me. The first time I saw this in a class, I didn't believe my next statement to be true, but it is going to be true. Okay, so you've all seen cosines and sines, right? You know what these things look like. Probably in your trig class, you did a lot of study of these things, and exactly what do they look like. Okay, so these signals, we can talk about the frequency of the signal. So this is something I'm sure that you've done before in some math class, right? We can have low frequency signals and we can have higher frequency signals, meaning that the sine and cosine goes up and down more often. So it turns out that we can represent arbitrary signals by an infinite sum of sines and cosines. So we take a low frequency sine or cosine, and then we go up, we double, and then we go up, we double, and then we have to give a weight. They're not all equal amplitude. So if we store some weights, so let's say this first one, we're going to put a weight of 1. This next one, we're going to put an amplitude or weight of 0.75. This one's got a weight of 0.5. We have to have some phase offsets in here too. When you add these things up, you get some other signal. So it turns out any signal can be represented as a sum of these. So rather than representing, where's my original signal that I want to show you? Rather than representing this kind of crazy original signal, we can represent a list of sines and cosines to represent it. Okay, so now what we're going to store is these weights. So I keep this, instead of keeping the original signal or their samples, I'm going to store this weight and this weight and this weight. And I'm going to have a vector of weights for my sum of these sines and cosines. So here's some examples. So this plus this plus this plus this, when we add these things up, we can get closer and closer to approximating this square wave. And if I want to get to an actual square wave, I'm going to need an infinite sequence of these things being added up. So here's this signal. This is close to what was coming off of that mandrel. Okay, now we're going to add up these things. And now some have higher amplitude and some have lesser amplitude. And we add all these things up and we get closer to our signal. Now, I have come to accept this to be true, but I don't fully get it why this should be true, that I can add up all of these sines and cosines. Now, those of you who are writing in the chat that this is an FFT and you've had classes on this, okay, maybe you get it, why this math works. For me, this is magic. Like you take a bunch of sines and cosines and they add up to anything you want. But it does. But you might need an infinite sequence of them. Okay, so where is a place you've probably seen this in your real life? Okay, all those weights I was talking about, that's here. We take our audio signal. So this is an audio spectrum analyzer. We take our audio signal, we break it into these sines and cosines I was talking about, and then on our equalizer, we show all the weights for all the different frequencies of the sines and cosines, right? So this is something you've seen. You can, yeah. So I see in the chat somebody's talking about this class. Whichever class they really teach this about, like somebody posted in the chat so people can go take it if they want. I suspect that class is going to be a lot more mathematical and a lot less pictures than what am I showing you today. Yeah, it should be signal processing is what this is typically called. Okay, now how are we going to compute this thing? Like, where do we get all these weights from? So how do we compute this signal? Okay, so somebody was saying FFT. The FFT is the fast Fourier transform. So Fourier is a guy, and he figured out this Fourier, and so it's named after him. There's a Fourier transform. FFT is the fast Fourier transform. It's a way to compute this thing rapidly. When we write down the Fourier transform in the math, it's not the fast way, right? It's just the math. But there's some magic computation in order to make it. I don't even know the algorithm, right? So like probably instead of being in squared, it's in log in, or I don't know. Somebody who took that class and knows what the heck is FFT exactly can write that down. I just use it. I don't actually know how it's computed internally. So we have a signal. We add up all of these things, sines and cosines, and then we get to some other signal, right? So this is, you'll see it as a function, usually as FFT, and it's also called the Fourier transform. Okay, what is this Fourier transform? Now, if you'll go take that class they're talking about, you probably saw things that look like this. Now, here's a slide that makes my head hurt. Okay, so we're going to do some integral over our original function by something that I can't even quite figure out what the heck does this mean. And that's going to give us our Fourier transform signal, right, in continuous space. FFT is a discrete space approximation of this. Okay, and then recall that e to the I something is some cosine sine. Like what? Like seriously, I didn't take this class. Okay, if you're into this and this makes perfect sense to you, awesome. That's going to be useful to you in your career. I go find people that understand it. My head hurts by having these i's. This is the you know, this is I, square root negative 1i, right? But it's in here with my signs. Okay, anyway, there's some math that computes this thing. From the point of view of this lecture, yeah, whatever. Like we have to know how this thing works and how do we get rid of our aliasing. I don't have to know how to do the math. MATLAB knows. Okay. So we have a spatial domain. We have this Fourier transform. And that gets us something in the frequency domain. And then we have an inverse Fourier transform, which gets us from the frequency domain back to the spatial domain. So our spatial domain, I mean the real world signal that we're talking about, your image, your music audio waves, right? And they have some shape in the world, and we could take samples of this thing. And then we do this magic that converts it into sines and cosines, and we store the coefficients. And so here's my coefficient. So in this case, this signal is made of these three sines and cosines. And now my vector, I'm going to draw a picture of my vector. And so my 0th order has this much power. And then my next frequency, right? My next one has this much power, right? So this is here 4, 2, 0.75, 0.5, whatever they are, right? So I could have my vector storing these numbers. Here I'm just looking at graphically. What do those look like in terms of how this signal is converted to the Fourier domain? Okay, so what do these things look like? So here's a sine wave that's not centered on 0. And because it's not centered on 0, the average value shows up in the 0 component. So the 0 component, this is often called, if you're taking a double E class, this is often called the DC component, because they're talking about electrical signals. You know, you have DC electric and you have AC electric, and AC has a alternating current, so it's a sine wave kind of thing. So the DC component, meaning the non-zero weighted portion of your electrical current, often goes into here. So it's frequently called that even when you're talking about images. But anyway, it's the average component. And then because this is a single frequency sine wave, I just have a single spike. Now, why does it appear on both sides? This has to do with phase and those imaginary numbers, and like, don't worry about it. The two sides look like the same. In fact, I'm glossing over some stuff about those imaginary numbers. These peaks are the magnitude of what's going on. They're really complex numbers so the weight factors, how much sine or cosine, there's really a complex number specifying the weight, not a scalar value. But when we draw these pictures, we take the magnitude and put a scalar value. If we take a square wave, we end up with something that looks like this. And so we have a lot of power in the low frequencies, and then the power drifts off, and we get lower and lower stuff in our vector going out to higher frequencies. And importantly, this doesn't really cut off. It goes out infinitely. So that's a big deal, that it goes out infinitely. If we take a real-world signal, it kind of looks like this square wave, right? We have a bunch of stuff. It's hard to interpret. They always look like this. You usually have more power in the low frequency and less in the high frequency, unless there's something special going on. Okay, let's consider some specific examples. If I have a square wave or a box, right? This is later when we talk about convolution, we're going to call this thing a box. A box turns into a special function called a sinc. A sinc goes out infinitely. If we take a triangle wave, notice that these mid-frequency things have been cut down substantially. We have 0 and low frequencies, and then we have almost nothing as we go out, but this also goes out infinitely. If we go all the way to a Gaussian, it drops off nice and cleanly. It also goes out infinitely, but a lot less magnitude. So in some sense, if I had to chop this signal off and throw away some data, this stuff might be safe to chop off. It's a bunch of zeros. If I start chopping off here, it looks like there's real signal there. So somehow chopping off a sinc, not an ideal solution. Now, we're going to remember that. We're going to come back to this point, that chopping off this infinite extent becomes a problem. And remember, sincs are related to box filters. We'll come back to this. So now in 2D, what does this look like? Okay, remember our equalizer from our music. Here's an image. And by the way, this is the professor. So I stole these slides. You may notice that maybe I shouldn't say steal. I curate a deck of slides for you guys by looking at lectures from lots of other people, and I sometimes make up my own slides, and I sometimes curate slides from elsewhere. And so this guy is the professor. This is Kayvon, so that I happen to take these slides from. So anyway, the picture of him, and here's the spectrum. So we call this thing a spectrum. This is the frequency domain of this picture. So if I take this picture, do an FFT on it, Fourier transform, I get to this thing. If I did the inverse Fourier transform of this thing, I'm going to get back to this same picture. And notice this same pattern. There's a lot of low frequency stuff. There's less high frequency stuff out here, kind of like the other pictures we saw. In the spatial domain, what if we had just nothing? It's just blank, like it's just gray. Well, that's going to be a single dot at the 0, 0, the DC component, because it's shifted off of 0. And there's no other frequencies in here. If we put a single sine wave in our original picture, so this is a sine wave waving up and down in the x direction only, then we're going to get 2 additional peaks that relate to this sine wave. Because remember, I said it was mirrored across for a mathematical reason that we won't worry about here. It's always the same, mirrored across. So this is the one peak, which has to do with whatever this frequency was. And if we change this frequency to be a higher frequency, then this peak moves out. Remember, these are the higher frequencies out here. This is lower in here. So this peak moved out. When I changed this signal to be higher frequency, things moved further away. If we switch direction, okay, they're in the other direction when we talk about these 2D Fourier transform. And if we have some kind of more complicated signal that's got in both directions, okay, now I got peaks going out in both directions. There's just some examples so you can kind of try to get a flavor of what's going on with these sine waves with something that only has 1 or 2 sine waves added up, so that we can see what's happening. Now, what if I have something like this is a Gaussian? What if I have something like this Gaussian fall off kind of thing? So I have in the spatial domain a Gaussian dot like this. In the frequency domain, that has relatively low frequencies to it. And if I make this thing bigger and blurrier, then I have even lower frequencies that are in my content. If I squish it, then it's going to squish in one direction. If I make it diagonal, it's going to be diagonal. Like, is any of this helping you? It's helping to give an intuition of what's going on in this frequency domain. All of this kind of low frequency blurry stuff exists in a small region here, right? This high frequency stuff, we'll have to come to some examples in a minute.